Hello guys, welcome to Physics Grad. This is the third part in our series on the Legendre Transform, and in this video we are going to discuss some of the important properties of the Legendre Transform. So far we have seen the mathematical formulation of the Legendre Transform, which says the following: for a convex function f of x, the Legendre Transform is given by f star of p, okay, is equal to max with respect to x, px minus f of x. So see that I have changed the notation here to follow the general convention followed in various literatures. Okay, so the slope of the family of tangents here is represented by the letter p, and the transformed function is represented as f star. Okay, so here this particular operation, that is max of x, means we have to evaluate this function at the value of x where px minus f of x has a maximum. Okay, all of this has already been explained in our previous lectures. And one more thing, which is just some names, is that p is called the conjugate variable of x with respect to the Legendre transform. Okay, so when you perform a Legendre transform, you get a function of some variable p, which is called conjugate variable of x. Okay, this is basically the slopes of the tangent to which slope of the tangents to which f of x is the envelope. All right. Okay, good. So now I'm going to discuss two of the important properties of Legendre transform, especially for a strictly convex function. Okay, so properties. Okay, so the first property that we will look into is that Legendre transform of a convex function is convex. Okay, so to see this, consider f of x where f double dash of x is greater than 0, which means it is convex, and that too it is strictly convex because there is no equal to sign here. Okay, we will see what happens when f double dash of x is greater than or equal to 0 when we take some examples in the next video. Okay, but for now, if you consider such a function, then for a given p naught, say, let x naught maximize p x minus p naught x minus f of x. Okay, so this would imply our Legendre transform f star at p naught will be equal to p naught x naught minus f of x naught with f dash of x naught equal to p naught. This we have already seen in the previous lecture. This is the way Legendre transform is done. Okay, so this implies from this relation x naught is some function g of p naught, which is nothing but the inverse of f dash inverse of p naught. So therefore we have g of p, okay, is equal to f dash inverse of p. This again we have already seen. Okay, so this would mean that f dash of g of p is equal to f dash of f dash of f dash inverse of p. Okay, this will give f dash of x, which is equal to p from this relation. If you use x naught, this will be p naught. Okay, fine. So when I say f dash of f dash inverse of p, the value of this corresponds to the x value which maximizes this function. Okay, it is not any random x value, it is the x value which maximizes the function. So if our p is p naught, then that particular x value will be x naught. Okay, all right. So this would imply, okay, so we have f dash of g of p is equal to p. Okay, that's basically, so if we take p naught here, we get p naught, which means for any p we'll get p. Okay, so this would mean if I differentiate this function again, d f dash of g of p by dg of p into, using chain rule, dg of p by dp is equal to dp by dp is 1. Okay, differentiating this with respect to p will give you 1. So this would give dg of p by dp is equal to 1 by, so f dash again differentiated with respect to its argument is nothing but f double dash of g of p. Okay, so let us just make note of this relation. Okay, so far it has been simply a mathematical playing around with mathematics, and that leads us to this equation from the fact that this particular relation is satisfied. Why? Because that is how g of p is defined. Okay, because g of p is the inverse of f dash. Alright, so once we have this relation, let us consider the Legendre transform equation f star of p equal to p times, so max x p times x minus f of x. Now the value of x where px minus f of x takes the maximum value or maxima corresponds to, so x max corresponds to or is equal to g of p, that is from this relation. So whatever x gives the maximum value, it can be expressed in terms of p as g of p. Okay, so remember, this is not for all x, only the x for which the function has max is denoted using g of p. So I can write this as p into g of p minus f of g of p. Okay, now let us differentiate this function throughout with respect to p, or this equation throughout with respect to p. So that will give f star dash of p is equal to, using the product rule here, g of p plus p into dg of p by dp minus f dash of g of p into dg of p by dp. This is equal to g of p plus dg of p by dp, taking common p minus f dash of g of p. But we have already seen that f dash of g of p is equal to p, and therefore this will go to 0 because f dash of g of p is equal to p. That means our f star dash of p is just equal to g of p. Differentiating this again, we will get f star double dash of p is equal to dg of p by dp, which using this relation is equal to 1 by f double dash of g of p. Okay, but from this condition that f double dash of some argument is always greater than 0, it implies this is also always greater than 0. This implies f star double dash of p is always greater than 0, which implies f star of p is convex. Okay, and that is what the statement of the property is also saying. The Legendre transform of a convex function is also convex. Okay. So here the convex function is f of x. Its Legendre transform is f star of x. And because of this condition that we proved, f star of x is also convex. Okay. So that is the first property. The second property that I want to talk about is that the Legendre transform is an involutive transform. Okay. So Legendre transform is involutive. What does this term mean? Involutive means if f with Legendre transform gives me f star, then taking Legendre transform of f star will give back f. Okay. So it is reversible. Okay. So how do we prove this? So this implies f star star is equal to f. That is, Legendre transform of f star is giving back the original function. Okay. So for this, we will make use of the following two relation which we already proved when we discussed the previous property. That is, g of p equal to x equal to f dash inverse of p. Okay. Now remember, this x is the one which maximizes px minus f of x value. So we are going to use this relation and df star of p by dp is equal to g of p. That is this relation. Okay. So we are going to make use of these two relations to prove this property. Okay. All right. So let the conjugate variable. So let conjugate variable of p be q, which means now I am taking the Legendre transform of f star. Okay. So f star star of q. Okay. So f star was a function of p. Its Legendre transform will be a function of the conjugate variable of p, which is I am calling q. Okay. So this will be equal to maximizing over p the function qp minus f star of p. So this is how we take the Legendre transform for a function f star. Okay. Now, to maximize this, we have to differentiate this expression with respect to q. Okay. So let us do that. So first choose some q equal to q naught. Okay. Then f double star of q naught should be equal to max over p q naught p minus f star of p. Okay. So this maximizing means d by dp of q naught p minus f star of p should be equal to 0, which implies that q naught should be equal to f star dash of p. Okay. So the corresponding value p naught. Okay. So if when so this will be true for some p naught. Okay. So f star dash of p naught should be equal to q naught. That is, p naught is the value of p where this relation is satisfied. Okay. Because q naught is some constant, so we can't have p the value of p same. We cannot have for different value of p the same q naught. Okay. So what I mean is that when this left hand side is a constant, the right hand side must also be constant, and that means we have to choose some particular value of p corresponding to this value being equal to q naught, and that I'm going to call it as p naught. Okay, but now using this relation, which is d f star of p by dp is equal to g of p, this means this is equal to, so let me write it here. So this is same as d f star of p naught by dp, okay, or at p equal to p naught. This should be equal to q naught, which is equal to g of p naught. But our g of p, okay, our g of p naught is nothing but x naught. So our g of p naught is nothing but x naught. Therefore, our q naught is equal to x naught. Okay, which means f double star of x naught is equal to x naught p naught minus f star of p naught. But f star of p naught from our Legendre transform equation for f of x is what? So where is that relation? Yeah, so here. So f star of p naught is nothing but p naught x naught minus f of x naught. So we are going to use that here. So this is equal to x naught p naught minus p naught x naught minus f of x naught. This is nothing but f of x naught. So therefore f double star of x naught is equal to f of x naught. So for any x, so this must be true for any x naught, which means f double star of x is equal to f of x. Okay, so here this one we proved for some particular value of q naught which is equal to x naught. Similarly, we can choose other q values and come up with the same relation, which means it will be true for all the q values, and all the q values will be equal to all the x values, and therefore the Legendre transform of f star will give back the original function f of x. And this proves our property that Legendre transform is involutive. Okay, so in the next video, part 4, we will discuss some examples and note some important points when and investigate what happens when the function f of x is not strictly convex, or what happens if function f of x is not differentiable at some points, and finally what happens if f of x is not convex at all. Okay, so thank you for watching. See you next time.